Please welcome Bob McPherson of the Cal Poly Humboldt Geology Department presenting Kinematics of the Mendocino Triple Junction. Thanks for joining us, Bob, and please tell us a little bit more about yourself and your work before you get started. Take it away.
Okay. Can you see me? I don't see me.
Well, we see you, but you're not in full screen yet. So why is that? Maybe you can tell us a little bit more about yourself because we can hear you okay while we figure out what's going on with the.
Okay. I came here in the 60s and built a seismograph and carried it around this country, and I found that this area had a lot of earthquakes, none of which in 1960 you didn't know earthquakes were occurring here unless you felt them, and there were 3 a day basically. How's it going, Justin? Am I visible yet?
You are. You're full screen.
Oh, let me see. View speaker. I don't see myself.
You're on full screen. That's what we're seeing. You view in speaker mode, somebody says.
Okay. So anyway, what I want to talk to you all about tonight is the kinematics of plates, which means, it's a fancy word, confusing word, we have plates on the surface of the earth, lithospheric plates that slide around. There's maybe 20 or so large plates. And we happen to live by one of the largest plates on the surface of the earth, the Pacific plate. And I really enjoyed your introduction because the peoples have been living here for millennia. And all of what you see around you is, in our area, is basically the result of the interaction of these plates. So the terraces that Trinidad is built on, McKinleyville, Arcata, Eureka, the valley that Ferndale, Riadell, Fortuna are in, they're all related to the interaction of these plates. The tectonics made all these features. Excuse me. Table Bluff is a big fold in the surface caused by the interaction of these plates. So what I want to discuss with you tonight is I'm going to start out with an overview of how plates interact here at the Triple Junction, and then why we have earthquakes from that interaction of the plates. We had one just yesterday, and I'll talk about that one. But so that's what I'm going to talk about. What are subduction zones? What are lithospheric plates? How they interact, and so forth. And then I'm going to specifically go into 4 earthquakes that we experienced here on the North Coast. The December 20th, 2022, the twin December 20th, 2021. And then I want to talk about the Cape Mendocino earthquake in 1992 and the Honeydew earthquake in 1991. Many of you down in Southern Humboldt probably are very aware of these earthquakes, and they're very special earthquakes. Oh my goodness. Wow. I think I just saw someone that I haven't seen in a long time. So that's kind of the roadmap of my talk. And so I guess I'll start. Let me see here. Share screen. Okay. Okay, Justin, can you see the screen now? Or can anyone say that? Okay, and I'm going to get a pointer. Okay. So in this first slide, it's just a little eye candy. and I'll get back to it. It's a cloud of earthquakes centered on the triple junction made by Anthony Lomax, who lives in France. And I'm not going to say too much about it right now, but I'll show certain cross sections of it as I go along in the talk. So I'm just going to let it spin here for a minute. So the red earthquakes are December 20th, 2022 sequence. And the cyan are the previous year sequence of earthquakes, and then they're color coded by date. And that's all I'll say about this right now. I'm going to leave it a little vague until I get going. Okay, so there's the title of the talk, Kinematics of the Mendocino Triple Junction. And this slide is actually optic fiber. Over here on the left is it begins at the police station in Arcata, and over here it ends in Eureka. So this is 15 kilometers long. And we're using the optic fiber to record energy passing through the earth. This is an experiment that we're right now doing. And it's all on learning how to better warn citizens about shaking. So early earthquake warning system, and it's an experiment. And here's the players. This person right here is Jeff McGuire at USGS, and his cohort Andy Barbeau, and then others. Here's students from Humboldt, Carrie, Emily, and Otto, Amanda and Meyer, myself, Mark Hempel Haley. So this is the group, and we're trying to improve our earlier earthquake warning system by using optic fiber. By the way, this is the largest aftershock of the December 20th sequence, the 5.4, I believe. And it's shown, it comes all the way across this optic fiber, and these slanted lines are cars along the old Arcata Road. That's all I'll say about this slide. It's just a little teaser. Okay, so what I'm here to talk about is our subduction zone here, starting way above Vancouver Island and coming down to the Matoa River. This is Cascadia subduction zone. Over here on the very far left is all Pacific plate, as it is down here. So here's all this is Pacific plate, the largest plate on the earth. That slides around and is consumed all around the north and western boundaries of the Pacific Ocean. It subducts underneath. Here we have the Juan de Fuca Ridge, the Blanco Fault, the Gorda Ridge, the Mendocino Fault. And one of the things I want you to take away from this is the Blanco Fault, which is the direction of the Juan de Fuca descending under North America, is not parallel to the Mendocino Fault, which is the direction of Gorda descending under North America. And that's a problem. That's one of our sources of earthquakes, which I'll talk about more. That's what the consequences of the non-parallelness of these two transform faults is. It's crushing the Gorda plate. You can see the distance here is much greater than the distance here, and that's what Gorda has to get through. So Gorda is undergoing north-south compression, and we've known that since 1960. So that's one clue of what goes on in our area that is important. The other thing I'd like to point out is the subduction zone itself. So here in this cartoon that I drew from this site, here's the Gorda plate descending under North America. So this line here is the actual interface between Gorda and North America above it. And most subduction zones, all subduction zones are divided into primarily three areas. A lock zone, where the two plates are stuck together frictionally, and they build up strain as this plate descends by gravity underneath the overriding plate. A transitional zone, where it accumulates a little strain and then it slips, accumulates strain and slips, and then a constantly sliding zone where it doesn't build up any strain at all. It's constantly sliding. It's a ductile world. And up here in the cartoon, it shows here's distance measured in this overriding part of the plate. And you can think of this as accrued energy, also accrued strain energy. So it builds up over time until it can't take it anymore, and then it breaks in an earthquake. That's what happens in the lock zone. And unfortunately, so the lock zone over here on this map view is about right here. And we in Humboldt County live right above the lock zone, which is unfortunate. And anyway, and this is the transition zone. So we have episodic earthquakes now too. So that's how a subduction zone works. You build up strain by the descending plate, and once it can't take anymore, it releases it in an earthquake. Another thing to set up the talk is GPS stations. So all these white vectors over here are stations throughout Western United States where they're monuments, and the vectors are telling us how that piece of earth is moving relative to fixed North America way over past Colorado. So all these vectors are in relation to non-deforming North America over in Colorado or somewhere over there. And what I want you to take away from this slide is notice these vectors here. These are all moving with the Pacific plate. By the way, for reference, so here again is a Mendocino fault. So this is all Pacific plate. Here's the Gorda Ridge. So this is Pacific plate. So this big, strong, oceanic lithospheric plate, all the actions occurring on its edge. It's a very strong plate, and it has virtually no earthquakes within it. All the action is on the edges. And this is the edge right here, the San Andreas Fault. You can't see it, is buried. And you could see the influence of the Pacific plate goes all the way to Nevada. All these arrows, vectors, are pointed in the same direction, but they're decreasing in amplitude as one goes towards Nevada. And so you understand what's going on here. I have a, GPS 101 over here. So here's two stations going at different speeds, but in the same direction. And you can imagine that there's shear going on in between them if these are connected by a lithosphere. So if you got a station going 40 miles an hour and one going 20 miles an hour, you got a problem in between if they're all connected. If you have a station going slower than a station, say, south of it, then you're also going to have a problem. You're going to have squeezing going on in between it. And conversely, if you have a station going very fast and one going slow, you'll have stretching. So this is how we use GPS. And what's amazing about what we're learning with GPS is we're seeing the Earth strain, that is stretch, squeeze, extend in real time. And knowing these relationships, you can kind of figure out what's going on with the plates. By the way, notice too the rotation of the vectors as one crosses the Mendocino fault latitude into the subduction zone. So this lock zone, which I spoke about in the previous slide, here's the western edge of North America. This lock zone where the motion between Juan de Fuca and Gorda relative to North America is actually rotating the surface of the earth because of these interactions of plate motions. And then one other thing to know about our subduction zone or triple junction, here's some tomographic images and they're fairly complicated. So again, this is just like if you go into a hospital and you try to figure out what's inside of your head or what's inside of your chest or anything. It's the same technology. As a matter of fact, it was the technology from geophysics that we use in the medical world. It was all developed trying to figure out what's inside of the earth. So these are images within the earth for reference here. Here's the, here's the surface, and we're going down 1,000 kilometers, which is 600 miles, almost to, all the way through the mantle of the earth. For reference over here, here's our coastline, here's our triple junction. So this blue represents the descending Gorda plate. And notice it goes all the way up into Washington, and it's got some problems with it. So these are images, blue being fast, red being slow. These are images based on seismic velocities. And so we can look into the earth. And so this blue region here is Gorda descending down almost to 1,000 kilometers. Here's some pieces of older subductions floating around in the mantle. And by the way, this is the Yellowstone hotspot. So that's opposite of subduction. That's a rising plume. But so we can see within the earth, and I just wanted to show you this because it's important. This is what drives the subduction. This root of the subducted plate is gravitationally unstable and is actually pulling itself down. If I can go back, so it's actually pulling these plates down, and that's why you have these spreading ridges here. It's all because of this root descending in the mantle. And this is kind of mind-bending, I would think, because I'm telling you that there's a solid basaltic plate that's descending into the earth almost to the core mantle boundary. It's kind of hard to imagine, but that's what actually is the driving mechanism of subduction. And here's just another image by Karen Siglock when she did her PhD at Princeton. And it shows the same thing again. Here's the Gorda Ridge, Blanco fractured zone, the Juan de Fuca Ridge, Explorer Ridge up here. Here's our coastline. And here again is the blue is the descending Gorda plate. And in Karen's work, she found holes and pieces in it. So, but again, it's the gravitational instability that is the driving force that causes all of our earthquakes. All right, so getting closer to home, for reference, here's the San Andreas Fault around San Francisco coming up. It goes out to sea by Point Arena. It's offshore, and then it comes on shore for all you people down in Shelter Cove right there. I'll show some images of it. And then it ends right about the Mendocino Fault latitude. And here's the Mendocino Fault, which is the boundary between Gorda and the Pacific Plate. Again, here's the Pacific Plate. So everything over here is Pacific, and it's all headed towards the Aleutian subduction zone, Alaska. And what's important in this cartoon is this corner. This corner is imparting. Well, basically, Gorda is trying to get through this tectonic die, which it can't, so it's deforming. And I'm going to talk about these strike slip faults that are indicated by these lines with arrows. Here's another one going the other way. And so just for everyone's orientation again, so gorda forms off here, actually it's being pulled. And so new material upwells in the ridge. And then this plate is being pulled down and descends underneath us. And let me just go over the sources of earthquakes in this cartoon. So we have the San Andreas. So 1906 is a good example of what it can do. So a magnitude 8, 60 minutes of shaking. It's the boundary between Pacific and North America. We have the Mendocino Fault as a second source. It's the boundary between the Pacific and Gorda. Again, a strike slip fault. It can generate 7.5, so 45 seconds of shaking. We then have these intraplate within the plate, strike slip earthquakes as Gorda is being crushed. And these are left lateral, which I'll get to. They're magnitude 7s. We just had one. I'll talk about it. So I'll talk about the last 2 earthquakes, 2 of which were on these type of faults. So that's the 3rd source. The 4th source is these these faults within the North American plate. So I'll talk about the Honeydew and the Cape Mendocino earthquake. And then the 5th is the gorilla in the room, is the Cascadia subduction zone. So we have 5 things to worry about. Each one is a different size of earthquakes. Each one presents a different hazard. When I first started in the 60s, we didn't know that these left lateral faults existed. So this slide over here was a slide we made in 1980 for Terra Corporation, working to collect information on the nuclear power plant. And anyway, by 1980, we realized that these big earthquakes within the Gorda deformation zone down here, which I'll show you later, were left lateral earthquakes. And it was a major breakthrough in our understanding of what's going on. 1980 was the earthquake that really sealed the deal. 1975, I'm going to talk about in a little bit here. And this little panel here shows, again, if I can, so here's the corner of the Pacific plate, which represented here in the cartoon. And that corner is squeezing Gorda, and this is the result is this cloud of earthquakes. That's both in the North American plate, but primarily within the Gorda plate. So that corner right here is squeezing the plate, and it creates this cloud. And without that, we wouldn't actually see where these plates are. It's these earthquakes that actually tell us. So the crushing of the plate actually tells us where it is. All right, this slide came out in 2004 by Chater and people at Oregon State. And I just love it, but you can see the same details in Gorda nowadays. I mean, sorry, Google Earth. But this gives you the features of some of the intraplate earthquakes I'm going to speak about shortly. Again, for reference, here's the Gorda Ridge, and then it's kind of hard to follow, and then you can find it here. So this is where the plate's pulling apart by the sinking, gravitational sinking of the oceanic plate. And so new material is formed here, and then the structure is saved in this bathymetry image. You can see that the ridge and the structures are parallel to each other up here in the north. And then if you follow any one of these lines, you see something horrible happens. There's this big fold here, and then everything just goes to hell in a handbasket. And so it's like, to me, the way I view this is the top of the plate, the north of the plate, is acting coherently and is still subducting. But when the Blanco fracture zone, when the Blanco fault formed 5 million years ago, again, it put gorda in a vice, and it like put the brakes on down here in the south. And so the north continued to go, and it just sheared apart the south. And this is the source of our most predominant earthquake, is these faults, these left lateral faults in the gorda plate. And here, over here, I was trying to figure out how to use Adobe Illustrator, but it gives you kind of the details of the deformation of the gorda plate. And so I'm going to talk about some of the earthquakes that occurred right here that we felt in the last year. So those are the important facts to know what's going on. Again, here's the Mendocino fault down here. And it comes on shore right south of the atoll. I'll show you some nice images of seismicity. And notice it's a mountain range. So there's a lot of compression along this major strike slip boundary. Again, this is one of the sources. 1994, we had 45 seconds of shaking from an earthquake that occurred upon this section right here. And then notice too that the left lateral faults, these lines here, are actually occurring on these features that were developed when the plate formed. Okay. All right. So Anthony Lomax did an amazing job of relocating earthquakes. If I went back to that slide, looking at the earthquakes we located, looks like you're looking at it with no glasses. And then when Anthony relocated them, it's like putting glasses on. So they rearranged themselves along nice linear trends. Here's a linear trend, here's a linear trend, and here's the beautiful Mendocino Fault coming on shore right south of the atoll. It's just really beautiful relocations. So the red earthquakes in this map view are the December 20th, 2022 sequence. So the 6-4 was right here offshore by False Cape, and then it ruptured along this trend here to the east. This feature here came in 92, which I'll speak about. This is the sequence in Cyan that occurred in 2021, all coincidentally also on December 20th. It's a bad day. And it ruptured, it started to rupture the Mendocino Fault, then it jumped over here into the gorda plate. So a very complicated region. Oh, and by the way, so for those of you in southern Humboldt, here comes the San Andreas offshore. Beautifully, it's really well located now, and it comes right on shore in Shelter Cove. For those of you in Shelter Cove, you can go into the bay, and if you can see cobbles on top of bedrock in the cliff face there, follow those to the east, and where they end is the San Andreas, where it comes on shore. It's the one place that you can put your foot on one of the most major plate boundaries in the world as a line. It's pretty amazing. And then the San Andreas comes up, goes over Telegraph Ridge, and then we lose it. And for you people in Whale Gulch, here's the Whale Gulch. So the east side of the King Range comes up here also, and these are important. It comes up all the way to this region that I'm going to talk about in Cape Mendocino and the Honeydew earthquakes. So, okay, so The intraplate earthquakes, so the crushing of Gorda, this is what happened in December 20th. Again, here's the red. Now we'll look at it in section, so in depth. So for reference, 0, 20 kilometers or 12 miles, 40 kilometers or 24 miles. Deep, here's west, here's the top of the Gorda plate. All these little dots are the Gorda being crushed. But here comes the Gorda plate, the top of it, down, down, down to the west. And so you can see all the red earthquakes of December 20th were within the Gorda plate. So it was one of these intraplate vertical strike slip faults, left lateral faults. I'm not gonna, these are pictorial representations of the source. So this one is done by looking at waves. This one is done by looking at first motions. For all of you that know nothing about this, the important detail is notice this is a solution for a fault, and it happens to be left lateral, points towards the colored quadrant compressions. So I can determine that it's left lateral along a northeast southwest trend. And if we go back, it matches very well with this trend. So this is just another tool we use to figure out what happened at the source. So we know December 20th was a left lateral fault on a trend that's, let's see, what is this? 252. 252 is right here. So in other words, northeast, 270 would be right here. So along this trend. We also use GPS, and I'm not going to spend too much time on this. So these are stations in Humboldt County. And so all these stations move by these little vector arrows during the earthquake. So here's a representation of the aftershocks and what slipped. And these are the motions that actually moved on the surface of the earth. And we use these to help us, again, determine what's going on. And by the way, so this vector here, the largest one, is about 22 millimeters, which is an inch. So these are the ground moved in parts of an inch during the 6.4 earthquake. But again, this is tools we use to help us understand what goes on. This is done by Doug Drager, a friend of mine at the Berkeley Seismological Lab. And so he takes waveforms, and from the waveforms, he can determine how things slip during the earthquake. And for reference, so let's see here. I get confused looking at this stuff. Yeah, here's vertical depth. And then here's distances. So this is, the important thing is 10 kilometers. And so what I want you to get out of this is Doug determined that the slip patch was this big. And about 12 kilometers by what, 8 kilometers. So 10, 6, about 8 miles by 5 miles, a patch within the Gorda plate moved about 1 meter. And that's about right. That's about right for a 6.4. The magnitude is a combination of the area of the patch that moved and the slip of the patch and the rigidity of the material. And so anyway, this makes a lot of sense for a 6.4. By the way, a magnitude 8, this patch would be 250 miles long and 20 miles wide. So much, much bigger patch. Oh, and by the way, so here's the earthquake yesterday, and you can see that it's the moment tensor that I did for it. In other words, the source. Knowing the source, the depth, and where it sits in this aftershock sequence, I can say that this was an aftershock of the December 20th earthquake. And for those of you that live in Rio Dell and were around, excuse me, in 1975, the same thing happened on the same feature within the Gorda Plate in 1975. The cliffs fell down, chimneys fell down in Rio Dell and Fortuna. The pattern of damage to the cities was the same. And here's a map that we made in 75. Here's the 1975 earthquake. Here's the Humboldt Bay for reference. Here's the coastline. Here's False Cape, Cape Mendocino. Here's the Mattole River. So anyway, this sequence occurred with the same trend. I'm not going to dwell on it. Same focal mechanism. In other words, same source, same depth. Here's a depth section made in 1975. By the way, this is one of the first slides that showed the Gorda Plate descending underneath North America, made in 1975. But again, here's the 1975 main shock, and here's the top of Gorda Plate. So I'm just showing this to point out that this earthquake also was in the Gorda Plate. And if you look at a map of here's December 20th sequence, if I put 75 on that, there's 75 right there, fits right in. Same feature. So without dwelling too much on it, both the December 20th, 2022 and 1975 were on the same slip patch within the Gorda Plate. And this is new understanding, and it has consequences as far as how we view hazards. In other words, we're now, I believe that there are persistent fault generating, there's persistent faults within the Gorda Plate that generate repeated earthquakes over time that impact distinct areas in Humboldt County. So we've got to start thinking about this. All right, and the other earthquakes, this is more close to home in southern Humboldt, is this is this series of earthquakes shown here in this map. And it started in 1990 by this strike slip earthquake. Here's the Honeydew epicenter. Then there was an aftershock that woke Thomas Dunklin up. And in March of 92. And then here's the April 92 Cape Mendocino epicenter. And then here's the two aftershocks that occurred in the nighttime within the Gorda Plate. So very complicated sequence. So I drew this cartoon to help everyone understand, hopefully. For reference, this line here is the Mendocino Fault. So this whole surface here is the Mendocino Fault Plain. This is the San Andreas Fault Plain. So the San Andreas is offshore and it comes onshore north of Whale Gulch at Shelter Cove. Here's the Gorda Plate descending down underneath North America. By the way, this is a cutaway view so we can look at the 92 and 91 earthquake. Here's these strike slip faults within the Gorda Plate. Notice that there's oceanic crust and oceanic mantle. Anyway, everything above this line is North American plate. Everything over here is North American plate. And you can see by this cartoon, 92 ruptured out this way, lifted the coastline from about Brandstetter Ranch to the Mattole. and so Bear River to the Mattole, and Honeydew lifted Gooski Peak and King Range and Wilder Ridge when it broke, and I'll show you some slides of that. So these two earthquakes were North American plate earthquakes, which is another source that we have to worry about. So just to summarize Honeydew a little bit, here's the cartoon and an article. It's in Geology, March, April 1992. It's written for lay people. It's easy reading if you want to read about this earthquake. But anyway, it started at Dept, ruptured to the east, and shook Wilder Ridge and Honeydew area very strongly, which is characteristic of reverse earthquakes like this. They focused the energy at the nose of the hanging wall, this upper plate wall. And so there were tensional cracks. I'll show you some tossed boulders, all kinds of strong ground motions. What was really interesting in this earthquake to me was I interviewed some pot growers in Honeydew, and they said, "Oh, you're not going to take our," yeah, I'll listen to you. So anyway, these guys were walking up a trail. This is prior to the earthquake. They're walking up a trail to go to their garden, and they always stop at this spring and have a drink because it's they were going up 1,200 vertical feet, and they stopped at the spring, and the guy bent over and he was drinking, and he spit out the water, and that's terrible. What happened? You know, it's warm and it tastes like the river, and then all of a sudden the ground started shaking. And that made a lot of sense to me because I was there in the region looking for evidence of what happened. And one of the things I noticed was August 17th, 1991 was the end of a very dry period. So the Mattole was flowing at less than 30 cubic feet a second, and it didn't even make it out to the ocean. And then while I was out in the field looking around, it almost hit me like a 2x4. I noticed that people had chairs on islands in the river and things like that, but all of a sudden the river just started rising, boink, boink, each day. For 6 days it rose, and then at the end of the 6th day it was flowing at 80 cubic feet a second. And here's a little storm, and then it took about 2 months before, almost 3 months before it went back to what it was prior to the earthquake. So the Honeydew earthquake was very interesting. North American plate earthquake that had hydrologic effects, which is actually fairly common. Another thing with these North American plate reverse earthquakes is the strong accelerations at the nose. Let me back up here. At the nose here of both the 92, which would be onshore, and the Honeydew, which was inland, Wilder Ridge. So here's a socket where a rock on a river, this is Honeydew Creek. Anyway, here is where the rock was. Here it is now. Here's another one. This is where it was, and here it is now. So to do this, you have to have strong accelerations, and they have to be greater than 1G. Okay, so that was the Honeydew earthquake. I showed you this slide previously, and again here the red is the intraplate gorda earthquake. But here is what happened in 92. This band here, and notice it's sitting above gorda plate, like I drew in my cartoon. And so the earthquake started here and broke up towards the coast. And it lifted the coast, as a lot of you well know. I had some photos of Singley Flat, but Thomas Dunklin blew me out of the water with his photography, and he shared these with me, and I'm very thankful. So for those of you who know, here's the Russ property. This is Singley Flat. And going backwards here, so we're talking about the coastline here. So this wedge of earth went up into the west and lifted up the coastline. And my argument, knowing Singly Flat, is that this has been going on for a while. And this is probably evidence that this has happened in the past and it will happen in the future. This has been going on for at least 10,000 years, or as old as these higher surfaces. And by the way, and so the uplifted coast went from where my cursor is to north of this slide. And just some more images. Here's another image. You can see these uplifted terraces. So I think this is an argument that the 92 earthquake has repeated itself and has been doing this for a while. Just north of here, things really get, by the time you get to Bear River, things change. So this is definitely a block that's occurring. Yeah, and actually, I think I'll end there and take any questions if you have any.
All right, thank you, Bob. That was super informative and fascinating. I certainly feel like I learned a lot about that I didn't know about the Mendocino Triple Junction and the uplift in the King Range. So at this point, I have allowed folks to turn on their cameras and microphones. So if anybody has a question, we'd invite you to chime in and ask it, or to put it in the chat. I guess before we get any questions, I wonder if you could repeat where exactly, how you can find where the landfall is in Shelter Cove again? Of the San Andreas.
Oh, yeah. Again, I can't, let me see here. I can't see anything. Valerie. If you're in Shelter Cove, if you walk down the boat ramp, and if you get onto the beach and you look north, you'll see a cliff face. Of course, this probably changes with time. If you look at that cliff face, there's a boulder leg. So a whole line of boulders sitting on top of bedrock. And above that is sediments. If you follow that as you walk along the beach to the east, it ends. And where it ends is the San Andreas Fault, where it comes ashore. And by the way, it came on shore in 1906. It ruptured, and they followed the rupture up over Telegraph Hill, and then they lost it. I don't have time, but I think that the 92 and the Honeydew earthquake, and actually everything I showed you this evening, is related to the northern termination of the San Andreas Fault. And I don't want to make people nervous, but I'm a little concerned seeing what I'm seeing play out now. I think it's all related to the northern end of the San Andreas. And I think that the San Andreas is definitely responsible for the uplift of the King Range.
Fascinating. Looks like Thomas Dunklin has a question. Thomas, you want to ask that from your mic or camera on?
Yeah, sure. Just one comment. Yeah, Bob, thanks so much for interesting stuff, especially all the new graphics are great. Just one point of clarification is the zone of uplift began at Sea Lion Gulch, about a couple miles or a mile or so south of Punta Gorda. And then all the intertidal platforms from Punta Gorda to the mouth of the Mattole uplifted just as much or close to just as much as the platforms that we see at Singly Flat. So, just
no, that's a good point, Thomas. And I know you were with Carver and you guys were all measuring that. And yeah, if you looked at the cartoon goes all the way to the Mendocino Fault, which comes on shore south of the Mattole, which is very close to what you just said. And yeah, that all went up during the 92 earthquake, and you kind of lose it right around Bear River. It changes character, and then things really go up. So the block, you're right. The coast, yeah.
Yeah, there seems to be long-term uplift at Bear River because there's some marine terraces that are probably about the same elevation as the one south of the mouth of the atoll, right at the Cape Ranch, right? But we don't have any intertidal platforms, and the intertidal platforms were the things that created the bathtub ring of death that we could survey, the dead mussels and urchins and seaweeds. But without intertidal platforms, there was nothing to survey. So yeah. But anyways, just wanted to make that point.
Good point.
Thank you much.
So we got a couple other questions in the chat. A few folks saw our teaser about the candelabra trees and the hypothesis about that, Thomas, and Bob, sorry. And I wondered if you could speak a little bit on your hypothesis.
So there was an article in the North Coast Journal years ago about the candelabra trees. And the author, I forget who it was, wrote that they believe that the candelabra trees were a result of a windstorm. And that's a viable hypothesis, except I would expect it to be a much broader destruction than a linear row of trees. So I suggested an alternative hypothesis. Whale Gulch is an enigma. It's an amazingly straight feature. It's been mapped as a shear zone, but it doesn't go offshore. Anyway, long story short, I've seen candelabra trees next to strike slip faults down by Fort Ross. And my hypothesis, my explanation would be that they are fault related, not windstorm related. I think that the candelabra trees may have recorded an earthquake, a very strong shaking, centered on the Whale Gulch feature.
Great. And then somebody, Brad Ellis asked the question, how about uplift, the ridges, King Range? I think you might have spoken to that a little bit, but you want to speak a little bit more to that?
Yeah, the King Range, many people have studied the terraces, and Thomas just mentioned some of them. And he was with some of these early people that studied uplift rates in the King Range. The King Range is going up faster than almost any real estate in the world. And so everyone's scratching their head why. And I think if you go back to the GPS slide that I showed very early on, that everyone has memorized, there's, to me, it's all related to the San Andreas. I think the San Andreas, as it permeates into our subduction zone, is the effect. We know the effects of the San Andreas motion. Now, this is the largest plate on the earth, and the corner of it is shoving Humboldt County. And we see the effects of it all the way into Oregon. So it seems to me, when you're looking around for an explanation of the uplift of the King Range, and if you crawl around in the King Range, geomorphologically, it's saying, I'm going up fast. It's steep valleys, narrow valleys, it's not coherent rock going up 4,000 feet from the ocean. So it has all kinds of signs of fast uplift. And I think the culprit is the San Andreas. I won't bore you with, I don't have time to explain how I think that happens. But I think that's the culprit.
Thank you. Any other questions out there? Now would be the time. We invite folks to turn on their cameras and unmic them or unmute themselves, or put a question in the chat.
Yeah, don't be embarrassed by any question. Any question is fine.
Looks like Thomas, do you have another question?
Oh, no.
Well, Well, just you mentioned Whale Gulch a little bit, and we have this sort of tectonic fabric in Western North America that all follows the San Andreas, and Whale Gulch goes right into the South Fork of Bear Creek, which goes right into the North Fork of Bear Creek, which goes right into Honeydew Creek, which goes right into the Mattole, and it's all a perfect arcuate kind of lineament. And I think Lomax's seismicity really helps to show what's happening below the surface, but the landforms are reflecting this faulting that really shows at least a splay of the San Andreas coming on. So what do you think Whale Gulch is and Whale Gulch Creek and that
Okay, is it okay if I share the screen? Maybe to make a point. So let's see, share screen. Escape. How do I get out of this? I'm trying to get out.
Escape.
Yeah. Okay, actually, this isn't, well, let's see. I could go this way. I'm hung up, I guess. All right, I can answer your question without, I'll go back. So the San Andreas, it comes onshore at Shelter Cove, and then everyone loses it. One of the things I found in my years of going to the FOPs is when strike slip faults terminate, that is, we could look at the Garlic Fault, for instance, or the San Andreas, or for any strike slip fault. As they're propagating and they end, the tip of them rolls over. And my hypothesis is, my model is, and it's in the guidebook, actually, the Friends of the Pleistocene guidebook, is it rolls over and goes up Whale Gulch as a west dipping shear zone, and it rolls over and follows the coast, and no one's found that leg of it, and it dips to the east, and both of those planes go right into 92 and Honeydew. And so Honeydew and the 1992 earthquake, I think, are manifestations of the San Andreas Fault. And that's what bothers me right now, is because it's been 100 and some years since it's moved. And if what I'm thinking is true, well, I hope I'm not right, actually, because I don't want to go through another earthquake. But what I'm saying is that I think Whale Gulch is related to the San Andreas, and Bob McLaughlin's mapped it as a west dipping shear zone forever. And they all point to the hypocenters of 1991 and 1992. And by the way, all this other action is in the same vicinity. So if you think about, look at the Bay Area and the San Andreas Fault. What happened before 1906? All the adjacent faults for 50 years started going off before 1906. So what's happening here on the North Coast? This area where the largest aftershock of 1906, 1909 was the largest aftershock, is in this area that I'm discussing tonight. And then we have these other earthquakes. So, and I think they're all related to how the San Andreas terminates. So I hope that answers your question, Thomas. I think Whale Gulch is the termination of the San Andreas, or at least it's part of the termination of the San Andreas. But it looks like it, according to McLaughlin, it's an old feature.
Yeah, so, well, San Andreas is also an old feature.
Well, not the north end of it. It's a baby.
Yeah. Cool.
It looks like we got another question in the chat. Dale asks, if gravity is the force pulling these plates under the subduction zone and widening the ocean gulches, is there any theoretical point, however far in the future, that the weight pulling down will be more then friction holding back, and a big swoosh will suck these plates under. In other words, can these plates act like a handkerchief hanging over a table, and once more than 50% is hanging over, they slide into the Earth's core?
That's a great question. She should help me try to calculate whether that's even true. That's a very good question. It actually, that was a point I wanted to make. Oceanic lithosphere is really strong. It's got an average density of 3.3, and that's why it sits lower on the surface of the Earth. By the way, and these are all sliding around on some gooey stuff underneath the thickness of these plates. And so, yes, as it's the gravitational instability that actually pulls these plates. So if an oceanic plate is 200 million years old, it actually is going down into the Earth vertically. It's so unstable that it just is steep and it's going straight down. Our little gorda plate is very young, so it's still buoyant and it doesn't really want to go down, but its root is pulling it down. And that's part of our problem, is it really sticks to the North American plate well, which gives us bigger earthquakes. But to answer her question, I've kind of beat all the way around the bush. No, I don't think, I think it's going to work the other way. I understand her analogy of, yeah, once the weight of it is so great, it'll pull the whole thing down. That's a great question. But I think what happens, that's not a very good analogy as far as plate tectonics, because I think the opposite happens, is the plate starts warming up, so the pull gets less and less over time. So she has to come up with an idea with the pull becoming less, not greater. But that was a great question.
Great. Looks like we got another question too. Do quakes at depth at gorda plate indicate Cascadia subduction? What has more influence on the Lost Coast, the San Andreas or subduction?
Well, I threw a lot of stuff at you, and I was hoping some stuff would stick. And that's a lot of information was exchanged tonight. There's 5 sources we have to worry about. The San Andreas and Cascadia are the 2 big ones. You know, I always said that's the elephant and the gorilla in the room. So Cascadia presumably went off in January 26, 1700. Now that would be devastating because that's a magnitude 9. So that's 2 to 5 minutes of shaking. The San Andreas in 1906 was close to a magnitude 8, just slightly under. And that's 1 minute of shaking. We just had 16 or 15 or 14 seconds of shaking. So to answer the question, San Andreas and Cascadia are what I fear the most. But the 7.5s and 6.4s are more frequent. The good news is Cascadia goes off every 300 to 500 years. San Andreas goes off 125 to 200 years. Gorda goes off every 5 years. So, I mean, and you know, the last 3 times Gorda went off, they were far offshore. This one snuck underneath us a little and did considerable damage for a 6.4. It stressed my house out pretty good. Stressed me out pretty good.
On behalf of Friends of the Lost Coast and the Bureau of Land Management King Range National Conservation Area, thank you for tuning in to Lost Coast Lectures. To view the complete archive of recordings from this series, or to learn more about our work inspiring a passion for nature, visit Friends of the Lost Coast online at lostcoast.org.